Welcome back to Computer Lessons.
For over a century, the telephone was a device anchored to a wall by a copper wire. If you weren't in the room, you didn't exist. Today, that anchor has been severed, and we carry the entire internet in our pockets, constantly connected to a global hive mind. This freedom is powered by the most widespread machine ever built, the cellular network. The term cellular comes from the ingenious way engineers solved a simple physics problem. Radio frequencies are a limited resource. If a single massive tower covered a whole city, only a few dozen people could make calls at once before the channels ran out. To solve this, engineers divided the map into thousands of small hexagonal zones called cells. Each cell has its own base station and antenna tower operating at low power. The magic is frequency reuse. A cell in the north of the city can use the exact same radio frequency as a cell in the south because they are far enough apart not to interfere. This grid structure allows millions of users to share the same limited spectrum simultaneously. But this grid creates a new challenge: movement. As you drive down the highway at 100 kilometers per hour, you are constantly leaving one cell and entering another. The network must perform a handover or handoff hundreds of times without dropping your call. Your phone is constantly measuring the signal strength of nearby towers. When it detects that a new tower is louder than the current one, it negotiates a swap with the network core. For a split second, you are connected to both towers, and then the old connection is severed. A digital trapeze act performed invisibly. The first generation of this technology, 1G, launched in the 1980s. It was fully analog, meaning your voice was transmitted as a raw radio wave, similar to FM radio. The phones were the size of bricks, the battery life was terrible, and the security was non-existent. Anyone with a simple radio scanner could tune into the 1G frequencies and eavesdrop on private phone calls. There was no encryption, no privacy, and no data. It was purely a voice service for the wealthy business elite. The revolution arrived in the 1990s with 2G, specifically the GSM standard. This was the shift from analog to digital. Your voice was converted into binary code, ones and zeros, before being transmitted, allowing for encryption and clearer audio. 2G also introduced a side effect that changed human culture: SMS. Engineers realized there was a small amount of unused space in the control channel used for signaling. They decided to let users send short 160-character text messages in that space, giving birth to texting. Then came 2.5G or GPRS, which introduced packet switching. Before this, a data connection required dialing up like a modem. GPRS allowed for an always-on connection, paving the way for the very first primitive mobile internet experiences like WAP. 3G was the broadband era. Launched in the early 2000s, it increased speeds enough to make loading real websites and downloading music possible. However, when the iPhone launched in 2007, the massive influx of data traffic brought 3G networks to their knees, causing global slowdowns. The industry responded with 4G LTE, or long-term evolution. 4G was a complete redesign. It abandoned the old circuit-switched voice network entirely. In a pure 4G network, even your voice calls are just data packets, using a technology called VoLTE, or Voice over LTE. 4G made streaming video calling, and high-speed gaming a reality. It is the workhorse of the modern world. But as we connect billions of IoT devices, from smart cars to streetlights, 4G is hitting its limit on density. Enter 5G. 5G is not just faster 4G. It is a three-headed beast designed for three distinct goals: enhanced mobile broadband, speed, ultra-reliable low latency, response time, and massive machine-type communications, density. To achieve the insane speeds you see in commercials, 5G uses a new part of the spectrum called mmWave, millimeter wave. These are incredibly high frequencies, above 24 gigahertz. They can carry massive amounts of data, rivaling fiber optic speeds. However, mmWave has a major flaw. It is incredibly fragile. A millimeter wave signal can be blocked by a tree, a window, or even your hand holding the phone. To make it work, carriers have to install thousands of small cells on nearly every lamppost in a city. Most 5G, however, runs on sub-6 gigahertz bands. This mid-band 5G is the sweet spot. It offers better range than mmWave and better speed than 4G. It is likely what your phone is connected to right now if you see the 5G icon. The real game changer of 5G is not speed, but latency. 4G has a delay of about 30 to 50 milliseconds. 5G aims to drop this to 1 millisecond. This is critical for remote surgery or self-driving cars where a split-second delay could be fatal. To handle this traffic, 5G towers use massive MIMO. Instead of broadcasting a signal in a circle, the tower uses hundreds of tiny antennas to form focused beams. It tracks your phone and shoots a direct beam of data at you, increasing efficiency and reducing interference. Another key feature is network slicing. This allows operators to create virtual networks on the same physical hardware. Emergency services can have a dedicated slice that guarantees connection even during a crowded concert, while gamers get a low latency slice. But how does the network know who you are? That is the job of the SIM card, or subscriber identity module. This tiny chip contains a unique 15-digit number called the IMSI and a secret authentication key known as KI. When your phone connects to a tower, it doesn't send your password. Instead, the network sends a mathematical challenge. The SIM card solves the challenge using its secret key and sends back the answer, proving your identity without ever revealing the key itself. We are slowly moving away from physical plastic cards to eSIMs. An eSIM is a chip soldered directly onto the phone's motherboard. It allows you to switch carriers instantly by downloading a software profile, eliminating the need to hunt for a paperclip to open the tray. Roaming is another miracle of coordination. When you land in a foreign country, your phone contacts the local network. That network checks a global database called the HLR, Home Location Register, to verify that your home carrier will pay the bill, then allows you access. Security has come a long way since 1G, but threats remain. A Stingray, or IMSI Catcher, is a fake cell tower often used by police or spies. It broadcasts a signal louder than the real towers, tricking your phone into connecting to it so they can intercept your location and calls. Finally, we must address the health concerns. 5G uses non-ionizing radiation. Unlike X-rays or nuclear radiation, radio waves do not have enough energy to knock electrons off atoms or damage DNA. The only biological effect is a tiny amount of heat, far less than what is generated by your own body. While cellular networks cover the cities, they leave vast dead zones in the oceans, deserts, and mountains. To truly connect the entire planet, we need to leave the ground. We need to look up to the stars. In the next video, we will explore satellites, GPS, and the new space internet race. We will learn how a constellation of flying routers is trying to kill the dead zone forever.
Tell me in the comments, do you actually notice a speed difference with 5G in your daily life? Or does it feel exactly the same as 4G to you? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.